Okay, so Louis, if you can hear me, I see. Can you hear me? So good. Louis, so what do you think? Which points do you use to determine the rotation of a model? If you place these controls at the corners of the model, which points would you need?
So we'll use the B and the D.
For which rotation?
The hello.
For which
For
rotation?
the for the B and the D.
Which rotation are you going to use B and D?
Hello.
I'm listening to you. Go ahead.
Relative for relative. Hello.
I'm listening to you. Just carry on.
Yes, I'm saying that the B and the A for the relative orientation.
No, I don't think you are following what we're talking about. Yeah, we're not even talking about relative orientation at all. It means you are not here. All right, so
I'm here. I'm
because we are talking
following.
about the topic is absolute orientation.
My
So why are you
what
bringing a relative orientation?
the way my thing went off and I'm 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 following, sir.
Okay, fine. You are not quite, but
Hello, sir.
don't need to say you are when you are not. This is not about absolute. Absolute orientation should be mixed with relative orientation at all. So please don't do that.
It should be absolute. Okay, sir.
You wanted to say absolute, but then you ended up saying relative.
Yes, sir.
Okay.
Yes, sir.
Yeah. Okay. So so now your answer is that what B and D should be used for what absolute
We'll use
orientation. No, in absolute orientation, we have two types of rotations. We have the common omega rotation, which takes the model and then rotates it about the x. Then we have the common phi, which rotates the whole model about the y. So the question is that which of these rotations apply to which points on the board right now? Okay, so it will be difficult because so you go and read about it, refresh yourself. Is that okay?
Okay, sir.
Right.
Okay, sir.
So
Okay, sir.
that is basically it. I'm going to be talking about coordinate transformation so that we can be making some progress. Elections are around the corner, Christmas around the corner. There's no need to waste time. Obviously, coordinate measurements and transformation are very important because we're talking about model coordinates. We are talking about photo coordinates. In fact, here's fiducial coordinates and all those things. So coordinate measurement and transformation is a topic in photogrammetry that we cannot run away from. And one of the reasons is that the existing photography might have undergone some changes that as a result of environmental, elements, i.e. the elements, i.e. the temperature, humidity can affect a photograph. The creation of the diapositives can also cause there to be a change. Remember that we've already talked about interior orientation where some of these errors are corrected for. So it's very key that we take that into consideration in our coordinates, the coordinates that we are measuring. We need to find a way to correct it. Is that okay? All right, so that is what we will seek to do, and a few calculations in this one, and I think we should be okay. Everything about this write-up is good to read. Are you okay? All right. One of the things we touched on is the so-called the comparator, which is actually used for measuring coordinates. So you can obtain what we call the comparator coordinates. Okay, so as we are pursuing a program, we need to know some of the things that are possible. All right. So the comparator, I think there's a diagram on the comparator that I have not brought here, or it's not in this notes. I don't know if it's here, if it is, but it's not. So I will be sending it to you. I'll send it to you so that you have it. It's actually a device that you can actually place your photo on and then measure coordinates of it. So how that is done, we need to also read and appreciate it. I think we are talking about it here, but the diagram is missing, totally missing. Is that okay? All right. So read about a comparator and then how it allows you to measure. Okay, there are two axes to the comparator, and and then you can actually kind of read off. It's like some kind of dial or something like that. You can take readings. Okay, in the x and the y direction. Two orthogonal, axes. Okay. All right. So please read about a comparator. And then the processing of the measurements really have to also take into consideration, some of these formulas. This formula is not looking very clear, but when you actually look at it, there's a relationship between the fiducial marks and then the photo coordinates. Okay. So if you look here, x, a, y are image coordinates of the point in the fiducial system. Y prime a, s prime a are coordinates in the comparator coordinate system. So comparator, fiducial, and then the image or the photo coordinates. So here we are not using the word photo coordinates. We're saying image coordinates, but it's the same as photo coordinates. We need to appreciate the two different systems. The fiducial coordinate system allows you to, my whiteboard gets stubborn every Friday. I don't know. You write on it and it misbehaves. But the photo coordinate system is more like this. The photo is there. Then you have the y-axis, the x-axis. Okay, it's the fly direction. All right, so this is a photo coordinate system. A point A, somewhere here will now have coordinates ya, and then the xa. Okay, so that's the distance parallel to the x-axis. Distance parallel to the x-axis. All right, and so we can now measure along that. And then the y is a distance parallel to the y-axis, and we measure along that to meet the point of interest. Okay, with the x being a reference. Okay, so we measure s coordinate with the y as reference, because the sy axis, these two axes represent the origin of the coordinate system. So 0, 0, okay, becomes the center of the photograph, more or less, in a photo coordinate system, image coordinate system. Okay, so, oh no, this thing doesn't want to write. Okay, that's fine. So photo coordinate system. Right, and then you can have the fiducial coordinate system is also different. You can have the corner fiducials. These are the side fiducials. So these are side fiducials. Writing with the mouse is not easy. Side. The problem is that I cannot do it with my fingers. Fiducials. You can have corner fiducials. In that case, You have the photo. These are marks on the photograph that has been permanently done. Okay, so you can have the corners. We have here. Right, so if you have a way of marking the corners, then you have the corner fiducials. Corner fiducials. Okay. All right. So with the corner fiducials or the side fiducials, you can have your F1, F2, F3, I get that. So you can actually have F1, F2, F3, F4. So when you get the diagram I'm going to share with you with the comparator, you see the three coordinate systems, the comparator coordinate system, okay, which has an origin at the bottom left. So it's more like this. So the comparator coordinate system, your X is like this, your Y is like that. So Y prime. So if you have a point A, you'll be having X prime A, Y prime A as a coordinate, okay? And that same point will have three different coordinates. It will have X, A, Y, A as the photo coordinate system. If you superimpose the three systems, you will having one point having the same points. We'll be having XA, YA. Okay. And then you can now have the XF1, SF2. That also exists. It's a kind of coordinate system. All right, because it exists in a grid. That coordinate system can describe a grid. But this formula combines more or less. It integrates the three coordinate systems. Okay, so you can see that we have, let me point at them, comparator, image or photo coordinate system. Everything we have here will reduce our comparator coordinate system to a photo coordinate system. In other words, that is why we have this. Okay, XC prime minus XF4. So we need to appreciate this coordinate transformation even in using the comparator. Is that okay? So basically, that is a comparator, which is a tool for measuring coordinate system. There's also you see, we actually place the photo on the rotating stage. Okay, so the rotating stage also makes provision for correcting for rotation, I mean, in case there's the need for it. Okay, so when you do a rotation, then obviously this is how you compute for the angle of rotation if there is a need for one. All right, so that rotation will now convert our comparator coordinate system to a photo coordinate system in using this equation. Is that okay? All right, so there you go. A few equations. Now take note of this equation, this transformation. All right, we will visit it again. We will look at it again. So there is a shift in this particular relationship here, and then by here we have a rotation. So in every transformation, there is what? A shift, and then there is what? A rotation, and there's also a scaling. We will get to know that. All right, but we need to always remember the need for the transformation. The need for the transformation lies in the fact that there has been a change. Are you okay? has been a change in terms of maybe, like I said, it could be temperature or humidity or something like that that has caused that. And so some of the main causes of the errors, you can see them here: photographic material, IOK, the optics, refraction, FKVH, all the things we talked about. Okay, they demand that we actually able to correct for them, IOK, one way or the other. But coordinate transformation is also saying that there's been a general change in your coordinate system, and you need to apply that IOK so that you have the new coordinate system that you're working in. So it's like as if you are correcting for something that hasn't gone well with the photograph. But yes, so displacement of the principal point, I think we've talked about that as part of interior orientation. Comparator errors, obviously, formation of photogrammetric material. Please read and appreciate how these things work. IOK, non-uniform scale along S and Y axis, none of the gonality of the two boxes. I think I'm not to the way I'm pronouncing my words here. And then the curvature of the axis, etc. IOK, these will definitely introduce errors. Deformation, if there's water, humidity in the air, materials will definitely expand or contract, whichever way it goes. You don't want it. Temperature changes will always cause some kind of expansion. Okay, that will now change the coordinate system that you have. So all that require that there is a transmission, plastic flow, and all the agents. Just the fact that you've put photographic material down will mean that definitely is going to be a change. Are you okay? All right, so it brings us to the need for a transformation. And so you have one coordinate system that you know of, you have another one that you know of, and something happened, and that's why you have these two. How do we make sure that every coordinate here can be referred to in another coordinate system? Okay, so for example, in Photogrammetry2, we learn about the similarity. No, we don't learn about similarity transformation, but then in Photogrammetry2, we even learn something around that. Okay, around these kind of changes. Okay, changing from one in the total photograph to the vertical photograph, there was a change of a sort. There was a shift that we needed to take into consideration, and there was a rotation. But here we will recognize that in 2D coordinate transformation, we need to consider three things: translation or the shift, scaling, and then the rotation. Okay, it's a shame that my whiteboard isn't working, so I can't write anything for you to even appreciate. You just have to stare at it. Is that okay? Because writing with my mouse is not going to be easy. My fingers are not working. I don't know whether my hands are too. I don't know what it is. But translation means that you take a value and then you add to it. Are you okay? So we take this original coordinates, which means that the origin of the coordinate system has moved. So we now have to shift to the new origin. Then everything will be fine. But then we realize that even though we shifted to the new coordinate system, we still don't have things, at the same scale. Are you okay? So we need to now change the scale. And so we change the scale by multiplying by a factor, a scale factor, a scale change for the X and for the Y. Y axis, X axis. For the rotation, I told you that we'll be visiting it again. We just do a cos sign and a negative sign cos. Okay, you apply that to the coordinates, and then you will now have a new X and a new Y. Okay, so your existing coordinate system has coordinate S naught, Y naught, and then your new coordinate system, which is a transformed one, will now have Xn, Yn. Okay, but then they all make use of X naught, Y naught in the calculation in order to get the new coordinate in X or the new coordinate in Y. Okay, so this is how it works, and it's not going to be easy for me to actually try to even explain to you using my whiteboard, because it misbehaves sometimes. It's not consistent. It's not consistent. Okay, so otherwise I should be able to write X See, when you write, then it starts giving you dots. But it's okay. It's okay. Let's move on. Maybe another time I'll investigate and find out why it does that. Okay, because it's not nice to just show it like this. But I hope you appreciate it though, Luis. I know the boy is gone. They always do that. They're not serious. So scaling, like look at it very carefully and appreciate it. We multiply to scale, we add to translate, and then to rotate, we make use of the rotation matrix, cos, sine, cos. Okay, and then we are good to go. We'll be getting a new set of what? Coordinates. This is also known as a two-dimensional conformal coordinate transformation. Conformality has got to do with shape. Always remember that, and direction. So, but then if it's anything to go by, that is it. Is okay. Excuse me. So we take note of this rotation to make the reference axis of the two systems parallel. Second, two translations. So we do one rotation, two translations to create a common origin, the two systems. Then scale factor to create equal dimensions in the two systems. Okay. All right. So we can do anytime we need to do a transformation, coordinate transformation. This is one of the things that we'll be doing. Even in surveying, that is done. In pictures, this is how the translation is done. We move the origin. Scaling means we just multiply by a factor in every direction. Sx, xy, sx, sy, and then we change the coordinates. Then rotation is done this way in the two-dimensional coordinate transformation. All right. So in order to formulate it, then we have to write equations, okay, for all the three types of transformation. For example, in this equation, there's some scaling going on. There is some shifts going on. There's a shift in there. And then there is what? A rotation. Okay, so here's the shift. Let me get my annotation tool working. This is the shift. All right. This is the rotation matrix, everything here. This is the rotation matrix. Then we have the scale. Okay, so that's the scale over there, this one. All right, but really these are two equations. If you look at them carefully, then you realize that if we expand this matrix, then it's ax naught plus by naught plus c, okay, equal to xn. So we can always expand it and then get the equations back. Is that okay? All right, so scale, rotation, shifts, x and y, and then your final coordinates are xn and yn. All right, the original coordinates are always going to be s naught, y naught. Maybe we shouldn't have called them that, but we can do that if you want. All right, so that is it. Let me see if there's more we need to know. I think that is basically, once you get an equation, then you need to find a way to compute the parameters a, b, c, d. Okay, so like I said, when you expand it, this is what you get. There's a common scale that we need to, multiply the values by before we do the shifts. Okay, and then off you go. We can now rewrite this whole thing in terms of two vectors. We can write, so this actually a 2x1 vector given by a 4x2 vector times 4x1 vector row column. Okay. So I think I'll have to revise this again. 4 by 1. So 4, 2 by 4. Okay, so in matrices, once you write something like you cancel the 4 and the 4, you get 2 by 1. So 2 by 1 is equal to 2 by 4 times 4 by 1. Okay, so we have this situation. Trying to get some lighting here so that the video will look nice. All right, so we have this equation here. Appreciate the values. These are the coefficients. The A, B, C are the coefficients. We can solve for that. Once you solve for that, then we can now have a sort of machine putting any known coordinates, S naught, Y naught. Now you'll be getting the new coordinates, X, N, Y, N. Okay, but then you can't solve for this matrix because it's not a square matrix. You can't find the inverse of it. Because to find A, B, C, D, you need to invert this matrix. You need to invert this, but then you cannot invert this. It's not possible to invert this matrix. So you need to turn it into a square matrix. And the good news is that we can introduce more control. So for every control, we can write one line of equation. So for one control, you have x, y coordinates. So just one control can give us 2 lines of equation. So 2 controls can give us like 4 lines of the equation. Then we are working at something. We are getting somewhere. Okay, they'll be getting somewhere. Excuse me. All right. Trying to get to the next one. So here we go. We can have a reverse between the unknown. We can work out the unknown from the known, the known from the unknown. I mean, just substitution, turn it around, and then you'll be getting somewhere. Okay. So let me show you a typical example that we've done here. In the conformal transformation, what we do is that we have 2 coordinate systems. So here we have the map coordinate system, we have the ground coordinate system, and we can find out the relationship between the 2 coordinate systems and then have a transformation. Is that okay? So this can be, we can look at it in terms of georeferencing, so which you will learn later on, or you probably know already. Okay, so you have to now take 2 coordinate systems and see how they relate, and then you change all the unknowns when you find the parameters, the appropriate parameters. So you only need a few coordinates to transform a whole set of unknown values. Okay, so now, so here how many controls? We have 2 coordinates, 2 objects. Okay, so the first one is 1, the second one is 2, and then on the map, these are the coordinates on the ground. That's the coordinate. We put them, we form 4 coordinate equations, and then now we have a square matrix, 4 by 4 matrix. Okay, so this one we have 4 by 1 equal to 4 by 4 times 4 by 1. So we still kind of have, three matrices which are actually, at par, can be equalized. But then the good thing is that the middle one, we can find the inverse of it. In other words, we have to simply make one the subject of the other. So if matrix A is the first one, or even to use the right thing, the right formulas, the right variable names, x is equal to A times, the parameters there. I don't know whether we call it L or something like that. Then obviously we can find the unknown parameters. equal to x times A inverse. So, this is not -1. This is like A inverse. Okay, the inverse of this. If A is a matrix, all right. So there we go. We solve for this. You can use your calculator if you can. The calculator can do matrices. So anytime you're doing photogrammetry, at least get a calculator, get a computer that can do this. But if you were in exam, you go with a scientific calculator that can do matrices and find the inverse of matrices. All right, there we go. So what I just said is what is happening here. The inverse of the matrix, the middle, times that. Okay, these are the shifts. If you look at it carefully, these are the shifts. These are the cos, then the cos and the sine, the trig functions that make up, and then the scale. Okay, that's what you are looking at over here. All right, and then what did we just solve for? No, actually, this is what we've actually solved for the A, B, and C's. Is that okay? All right. So whichever way you look at it, you need to solve for the unknowns. These are shifts. The CX and the CYs are shifts. Okay. And then the AB. So these are coordinates within the one of the systems. All right. And then this is these are actually cosine of the rotation times the scale. All right. One and the other is the sine of the rotation times the scale. All right. So we work out the values that we don't know, and we're able to obtain this. All right. So in the affine transformation, we don't have a preservation of the orthogonality. Is that okay? We have a serious problem. The axes are not okay. They seem to have changed. They are no longer orthogonal 90 degrees to each other. So now we don't have a single angle of rotation, which is theta. We have epsilon and beta. Okay, so that is the problem with the affine. So the affine will always have to look at an image which is really distorted. Okay, and as the distortion increases, we will even find out that we just don't need an affine transformation. We also need to use other methods that work. But the affine looks similar to the similarity transformation or the conformal. Okay. So I mean, obviously, instead of having sine theta, you have sine alpha plus epsilon, etc. Okay, and then those changes are factored into the coefficients, and then we now start solving for the coefficients. Okay, and then the shifts are showing up as CX and CY. Okay, so yeah, there you go. Then you can also solve for that. Okay. All right, so that is the affine transformation for you. Okay. And then you can apply a polynomial transformation if you feel like there's more distortion. You introduce more, parameters. Okay. And that also means that we need to introduce more coordinate systems. More coordinates, control points. Okay, and then we can now solve for the unknown values. Okay, so the number of equations you have should reflect the number of unknowns. So in what you call a simultaneous equation, for example, the number of unknowns is 2. The equations are 2, x and y. Okay, as opposed to a single, solving for just x. 2x equals to 1. In the simultaneous equation, you have 2x equals to y plus 1, and you have to write another equation. Same way, here, the more values you have to solve for, then the more equations you need. So n equations and n unknowns need to be solved for. Okay, and then you can use the matrices. Okay, if this also doesn't work, so generally there are different forms of polynomials that can be applied. Okay, they're different. In fact, they have so many of them. All right, but you need to always take note of that you can overcorrect something, just like beating a child up. to correct them, you end up just killing the child. You don't want to do that. You don't want to throw away the baby with the bath water, as they say. So when there's so many points involved, okay, you also want to now start looking at what we call the least squares adjustment, which now looks at a large number of observations. Okay, and in this case, we need to have more observations than is required to solve the problem. That is the condition for which you actually start solving for, using the least squares adjustment, which I think you'll be taught in the survey adjustment class. You begin to appreciate what the values are. You talk about the residuals and the errors, okay, involved, and then you solve for the unknowns. Really, it's really interesting, isn't it? You also look for the reference variances and the etc. A weight matrix is also used. So we will not go into how this works, because then it will be digression almost. We'll be leaving photogrammetry. Let's assume we can apply those principles in photogrammetry. So I'll just leave it here for another. So basically today we talked about the coordinate transformation and how it's done. We need to always move. We may need to move from one coordinate system to the other. Model coordinates to ground coordinates is an example. Comparator coordinates to photo coordinates is another example of coordinate transformation. We just saw an example of map coordinates to ground coordinates. You could always have some, inconsistencies in there. Okay, so the transformation is not just done anyhow, but via mathematical models, and the simplest of them all is the similarity of the conformal transformation. And then as we move on, as the distortions that has been introduced get more complicated, we may introduce what we call the affine transformation, and then subsequently polynomial transformation, and the order of the polynomial also determines how warped our final image is going to look like, or photograph is going to look like. Then least squares adjustment comes. In fact, in photogrammetry, least squares is what is being used, what we call the bundle block adjustment, where we look at all the photo points, measure so many photo points and try to, carry out a transformation. Is that okay? All right. So that is it. If you have any question, you can ask. I think earlier in the lecture, the previous video, we talked about absolute orientation. I shouldn't forget to talk about that. In our next lecture, I think we are really moving fast, and then hopefully the earlier we finish, the better. There's one or two more topics to talk about, and our next topic is definitely going to be on stereoscopic coverage and bundle block adjustments. So read around it. It's a lot. They are not complicated, but it's a lot. Okay, read around it and get ready for the next one. So it's been nice. Do you have any question on so far what I talked about? You can ask. Otherwise, I think I will end it. Do you have any question? Okay, Louis, do you have any question? Or should we just say goodbye?
Sir, I'll read and see if there is anything I will.
Okay, please do. All right, so enjoy the weekend and
Sir, please, will you send the video to us? The video.
Yes, I'll try and upload it for you. Yeah.
Will you send the video again? Okay.
Yes,
okay.
yes, I'll do.
Yeah. Okay.
All right. So have a nice weekend. Bye bye.
Bye bye.
Okay.